welcome back. So in this video, we'll try and see how gradient descent works for the problem that we just set up. So if you look at this, you will see that I have given the data set here. So we are again considering the first order system, and I have given the data set which I had already shown you. And we have our initial guesses for A equal to 35 and B equal to 0.004. And we want to try to find the optimal coefficients for the nonlinear inverse problem. And we are going to use what is known as vanilla gradient descent. Forget about this vanilla. That means it's plain gradient descent. Let's go ahead and see what we did. Okay, so here is just like with the linear regression problem, I have just set up the data. This is the T data. I have taken a transpose here in order to make it a column vector. Right now, this is a row vector. Similarly, on the right hand side here, I have specified theta. You will see 3.1, 11.8, etc., etc. I have specified it completely. Okay. Now, I have also changed my variables in order for notational convenience. So I called x as t, just as I told you in the theory video, and y equal to theta. This m is simply, it counts how many there are. So that's 6. It will automatically come to 6. So now we can give some initial guesses for the parameters A and B. We also guess for alpha. Here, number of epochs, as I told you in the last videos with gradient descent, simply is the number of iterations that we are using. Right now, just to set our expectations, we are going to try 5 iterations. And I have set the values for A and B as 35 and 0.004. 35 and 0.004, as I said earlier, are from physical parameters. And now let's write down what the model and its gradient are. Now here is one place where coding shines over analytical expressions. I have given capital YH. This is the function, okay, which takes in x, a, and b and returns the value of the hypothesis function at that time. So as written here, this is a times 1 minus e to the power minus bx. This is exactly the model that we had specified earlier. And now I have written what dy dA is. Notice this is not dj dA. Dy dA is simply the derivative of this with respect to a, which was 1 minus e to the power minus bx. And dy dB, as we see here, is a times x, not a times b. It's a times x, e to the power minus bx. So all these we had seen in the video just before. So at this point, you can write down what a and b are. We can ignore this for right now, and we will run this code shortly. Now, here is what happens when we start doing gradient descent. Notice the final step. This is the most important step to notice. A is a minus alpha times dj dA, and b is b minus alpha times dj dB. And we actually calculate what a and dj dA and dj dB are. I have called this term as the error term because it's the gap between what our model predicts and whatever the value of y is. So we have summation of yh minus y times dy dA and yh minus y times dy dB. So this is just simply programmed in, and we can experiment with various values of alpha. So I'm going to run this code, and we can check what happens. So you can see that almost immediately it has jumped up. You can see that the value of b has now jumped up to 3000 something right from our initial guess. And as this happens to be a very unphysical guess. Okay, I can try reducing the value of alpha, but more importantly, let me just show you what happens step by step. If I take here and run this, I can check the value of dj dA, which is minus 5 point something. And I can also check the value of dj dB, which is minus 3.125 into 10 to the power 4. That's a really high value. And that's what is blowing this entire thing up. Okay, so if I continue, it'll give me really bad results. So I can see that maybe I should reduce the value of alpha. Okay, so let's say I make it 10 to the power minus 4. 1e minus 4 means 10 to the power minus 4, not e to the power minus 4, 10 to the power minus 4 within MATLAB. Again, this is stuck here, but I'll just continue. And you see this is a little bit smaller. But this also, these values that you see here of B also happen to be really high. If I continue for, let's say, 500 epochs, you will see it is just stuck there, and these are not actually very physical values. So this trouble tends to happen with gradient descent with nonlinear regression. Okay, so if I try other values, it still causes a lot of problem. I will spare you the details here, but what tends to happen with gradient descent is it doesn't quite converge to physical values with any sort of alpha for this problem. Now, there is a solution to this. There is a solution to this. You can actually find out some ways of solving it. So notice B was this, and B is really, really high here. Okay, so the B it is predicting is really high, and that happens to be quite unphysical. Okay, so I'm not going to argue from heat transfer right now here, but because my aim is to actually move on to a different algorithm which happens to work very, very physically for this problem. So what we are going to do is actually re-examine how we were solving this non-linear regression problem and come to a different algorithm called the Gauss-Newton algorithm. So we will do that in a series of steps in the next few videos. So I'll see you in the next video. Thank you.